All right, welcome back after the coffee break. Let's continue this session on galaxy formation. So the next speaker is Arturo Nuñez, who will talk about the Mochimasi simulation, 6 cosmological simulations of the same spiral galaxy, the impact of baryonic physics. So please go ahead.
Great. So, well, hello. I want to thank the organizers to letting me talk in this round meeting. So yeah, as Oscar said, I'm going to talk about a bit of the Mochimasi simulations. The Mochimasi simulations are named after the beach I have here in the back. And the idea was to do exactly the same initial conditions and just change the star formation and the feedback strategy to see how the simulation was going to suffer. And well, basically what we did was to run a big box, a small box, actually, a 35 megaparsec box that goes to a resolution all the way down to 35 parsecs in the zoom regions where a Milky Way-like galaxy would be simulated. And what we use this code called Ramses. You maybe heard of it this week. And our initial conditions are for music. Then the idea was to test 2 more or less benchmark or mainstream supernova feedback, so the delay cooling and the mechanical feedback. And then the classical star formation that we all use, in which basically the star formation efficiency is fixed, and you just impose a density threshold, maybe even a temperature threshold, to form stars in the right section of the gas. The idea was to compare this with this turbulent star formation scheme, where basically the efficiency is now calculated from hydro parameters. Now, okay. So, but you all know the feedbacks. We're using the delay cooling simulation by Romain and Johan, and then we're confronting it to the mechanical feedback by Tyson. Then we get these 2 star formation say strategies, in which, as I said, you get the classical way of forming stars, and you fix your star formation efficiency. Either you follow somebody's way of calculating this efficiency, or you just play until you get the right mass. And we confronted to the turbulent star formation strategy, where then this efficiency is going to be depending on the turbulence of the local gas. And you get one final free parameter, which is this epsilon here, for which we test 2 different values, 2 extreme values, okay? What we get are these 5 galaxies, and I said 6 simulations because we also have a dark matter only one that it's gonna play a role in the second part of my talk. Sorry, I didn't put the watch, so I'm gonna try to follow my time a little bit late. And so basically, as you can see, we get a disk all the time. This is more or less by design, because we searched for a disk at the beginning. And at least by changing the different baryonic physics, the disks are not destroyed, but they change considerably. One of the important things is, for example, that is this case that is a little bit catastrophic when you look at the bulge, but you have a bunch of clumps, of star-forming clumps that you will see in the gas and in the stars that are quite interesting. This case as well with the delay cooling and already turbulent. So all of these runs, sorry, have a turbulent star formation. The only one run with a fixed star formation is this one that is called K's law. It's based on the Keneco-Schmidt law, or you tune it so it follows the Keneco-Schmidt law. And all of these ones have the turbulent star formation. Another way of looking at this is here, where you can see edge-on and phase-on view in luminosity at the top, density of the gas in the center, and temperature of the gas in the bottom. And as I mentioned before, there are a few differences that are very apparent, but one of the things that I like to highlight is the fact that here you get some clumps, even though in this case they're a bit catastrophic because they're ultra efficient at forming stars, so you get super bright central bulge. And there is this case of the delay cooling that looks quite well when you do these skirred maps with luminosity. It's a bit more, it's a smaller and more compact gaseous disk, and it's not as hot as the case with the mechanical feedbacks. So another interesting way of looking at this, it's when we talk about this star formation threshold. that basically for the fixed star formation, you impose a hard threshold. So what I'm showing here is the phase diagrams. You have density and temperature, and you have all the gas cells inside the galaxy. So what you can see is, okay, so cold dense gas should form stars. You impose that here in the case of the fixed star formation, but in the case of the turbulent star formation, we did something a bit wild, which is to let this threshold be very, very small and see where will this turbulent star formation form stars. And we see that it's more or less okay, except for some cases in which we are forming stars in a region that is not expected to be forming gas, but it's not a lot at least. Now, if we look at our galaxies in the stellar to halo mass ratio plot, this classical plotting, which we compare with observations that are shown here in gray points or black points. The black points correspond to satellites of the Milky Way, and the gray points correspond to a very careful study of massive disks. So we can compare our central galaxies to this. Also, the lines under error bar and the error bands correspond to several studies, detailed studies and theoretical predictions of how this relation between the halo mass and the stellar mass should work. Then we put our galaxies here and we see that, okay, the central galaxies are more or less okay. The difference between the squares and the circles are basically how do you select your stellar mass, whether inside certain radius or inside the virial radius. And then we can look at our satellites. So all the small subhalos that have, the small dark matter subhalos that have a baryonic counterpart, and they look a bit like in the horizon plot, so they are a bit more massive than the predictions. Even though if we compare to some of the observations, that most of them are in the ballpark, there are a few simulations that actually keep quite well with the theoretical curves. Okay, so if we go on, we can disentangle between the different approaches by looking at the star formation history. See, so in the left, what I'm showing you is so basically these two plots go. The time goes towards the left. So beginning of the universe, end of the simulation, it's at the left, and beginning of the universe at the right. And if we look at the integrated mass, so the total stellar mass of our galaxies, what we see is that the two runs with mechanical feedbacks fail a little bit to constrain the star formation at early times. So at this cosmic noon that Jeremy was talking yesterday, we are forming a lot of stars when we use the mechanical feedback. And so if we compare our simulations to the prediction lines, which is this black line, which is taken from Berossi, we see that we are forming way too many stars, even though then the mechanical feedback basically starts working and plateaus the star formation. And if we want to disentangle between the star formation approaches, we can look at the actual instantaneous star formation rate. And we see that by the end of the simulations, they're very well disentangled. The turbulent star formations tend to form at a higher rate than the fixed star formation. Of course, this fixed star formation has been fixed by us, so I'm sure that if you play with the efficiency, you can get it up. But it's quite interesting that here we can disentangle them. Now, we're very worried that this early star formation is basically forming these massive bolts that it's not going to allow the bar, but as we know lately, the bar formation, it's a very complex issue. So, well, now we can look at the dark matter, which is, so everything I've shown you so far, it's results that we have already published. And now I'm going to show you results from an analysis that should be published soon, should at least be in archive soon, which is the analysis on the dark matter distribution of our galaxies. In these cases, basically what we start looking at the dark matter profile, which typically it's coded at what's called the dark matter resolution or the power radius, which is a very conservative inner limit of the resolution of dark matter simulations that we kind of consider to be maybe too constringent. So we also take this second line here, which is 3 times the size of the smaller cell. And here we see that if we look inside, the different halos are actually disentangled. So we start seeing an effect on the dark matter from the baryonic physics, which is really, really interesting. We already saw, and we have a whole paper on it, that the baryonic physics are going to change and sometimes even drastically the baryonic distribution, so the stellar distribution of the galaxy. But now, more interestingly, it's changing the dark matter distribution. We see that the central profile can become steeper depending on the baryonic distribution. So this we can, for example, relate to the size of the bulge that I'm showing here on the right. This is the density profile of the inner bulge, so the very inner galaxy. Sorry, you cannot see the units, but this is KPC. And we see that the denser the stellar bulge is, the steeper the dark matter profile is going to be, which is not crazy. Basically, you're getting a contraction through the presence, the basically gravitational presence of the stars. It has been argued that maybe if you have a very strong feedback, you can be able to basically turn this type of a cusp into a core, but we did not do any of this with our feedback. We might try in the future. Here, what I'm showing you is the same profiles but separated in blue, and with red, I'm showing you the baryonic profile. And as we can see, the moment in history, so basically this is the history of each profile. So the clearer the color is, the older the profile is, all the way to redshift 0. And what we see is that when they start crossing, basically the dark matter profile, the one shown in blue, it's going to become steeper. So again, we see a direct effect on the baryonic presence. One of the other things we did was a very careful fitting, because I found out during my PhD that basically every time I fit, if I'm not careful, I can have a goodish fit that it's going to be very different from the fit I did before. So here I try to compute using Bayesian analysis the error on the fit too, which is what I'm showing here. So there is an error band in gray from the data that is in black, and then there is some sort of error bars on the points that are coming from a fit. This is just to illustrate that the fitting a dark matter profile with an NFW kind of function, it's something we have to be careful with, because it's
3 more minutes.
Cool. So this is the rest of the profiles. Now another interesting thing, it's you can look at the shape, and here you see the dark matter only run, and as soon as we put baryons in it, the dark matter shape drastically changes. So we can look at this more efficiently by basically diagonalizing the mass tensor of the dark matter halo and computing this sphericity parameter or triaxiality parameter, where we can see basically that in the inner part of the halo, basically the distribution of the stellar disk is going to shape the dark matter, and in the outer part of the halo is actually the survival ability of the subhalos for against the central profile, that it's going to shape the triaxiality of the halo. So once we see this type of results, it becomes really interesting to actually study the subhalos of each galaxy. And if you remember the Aquarius paper, there is a prediction in which subhalos should follow the number of subhalos above certain math should follow this slope, which we see in all of our runs. But there is a small caveat. So in solid, I'm showing you the subhalos that all the subhalos. And in dashed lines, I'm showing you subhalos that are only dark subhalos that have not a considerable amount of baryons. And we see that there is an excess in this distribution. Typically, at the bottom part, the most massive subhalos are able to form stars. And some of them, depending on the run, particularly this run with mechanical feedbacks, are able to survive more efficiently the central harassment from the potential. So of course, this requires a careful study that it's going to be coming soon. So now I have arrived to some sort of summary and/or conclusions. The main message here is that the implementation that we use of baryonic physics will matter, and will matter for baryonic matter and dark matter. We have done careful tests on the baryonic distribution on the main halo, on the main dark matter halo. And what we see is that we really need to understand what's going on here. But this, of course, you all know, this is just a good test study for all of this. In the coming times, we're going to be testing different combinations of our feedbacks and even AGN feedbacks Also, we are looking for more candidates because, well, statistics are never hurting when you want to know what's going on. So thank you very much. And well, I'll leave the summary and the conclusion here.
Okay, thank you, Arturo. Questions? Let me see here. Do we have any questions? I see hands. Tayson.
So on behalf of Oscar, I'm I can't help but ask the have you looked at the metallicity of the satellites?
No, that's actually something we have not looked yet. Is there something you'd like to see so I can keep it in mind? Or?
Yeah, so it will be interesting to see what level of how meta rich your satellites are compared to the local analogs.
Okay, so for the satellite analysis, that's nice because that's something I'm working on right now. So thank you.
Thanks.
Sam?
Yeah, thank you for the nice presentation. I have a question about what IMF and supernova progenitor mass you chose.
So we're using IMF, the Chevrier IMF, and the progenitor, it's above 10 solar masses, 8 solar masses, sorry.
8 solar. So do you have a, I think the feedback,
most of the stars are
mechanical
really more
feedback,
sorry.
Sorry. So I think the mechanical feedback is not strong enough to suppress the star formation at the central region currently, I think. If we can increase the supernova energy, then
yeah, it's actually been boosted for our runs. It's been boosted by a factor four that we did with some tuning in the early stages of the simulation. And yeah, we might try the higher boosting, but at some point it seems like cooking.
Thank you.
Okay, I'll ask a question then as well. So you probably mentioned this, but now you have all these different feedback models, star formation models. But if you had to pick a favorite, right, or which one would it be?
Yeah, but this is a good question because it depends who you're talking to.
Mm.
So basically, I would say the one that it's most efficient is basically using the turbulent star formation with a string, very very strong epsilon cut with a delay cooling. It works really really well. The final galaxy looks very realistic, and it when you compare it to the Milky Way distribution, it's quite successful in different tests. But when you use the mechanical feedback, you get these clumps. So lately, I've been thinking that maybe using not such a hard cut on the epsilon of the turbulent star formation, but using the mechanical feedback might help us get a gas rich at early times and maybe clumpy galaxy. So this is some of the tests that I'm trying to start soon after hearing all of these talks with clumpy galaxies.
Okay, Sukyong.
Hi. Have you checked the spiral structure? Does the spiral arm structure feel the impact of the different use of the baryon physics?
I mean, only by eye. So, but this is something I've been thinking a lot about, because you can see, for example, there are cases where the baryonic arms are not really shown in stars, like these cases, and then some cases where you see very well formed spiral arms. So yeah, this is something I would like to test in the future. I'm not prepared. I have some codes to do it, but I haven't tested them. No, I mean, not formally. That's a really good question.
Okay, any final question? Sound again?
Yeah, thank you. So just a short question. Did you make these mock images using same parameters? Right? Same
Yes,
scales?
they have it's exactly the same code for the skewed images. I think, yeah, I got help from
very
JC.
different.
Yeah.
It's interesting. Thank you.
I agree.
Okay, let's see. Sukyong, is that an old hand or a new hand? It's an old hand, probably.
Old end.
Old hand, okay. Okay, then, okay, thanks again for this very nice talk. Let's go move on to the next speaker, Maxime Rey.
Yep.
We'll talk about the CGM as a constraint for star formation and feedback subgrid models. Thank you. Please go ahead.
Can you hear me or not? No, you can't hear me. Then my right. Can you hear me now?
I think you have some microphone issues, I think, or
Yeah, John, I have microphone issues.
We lost you now, but yeah. Okay, microphone issues with Ubuntu. Yeah, try to see if we can solve it for, yeah, exactly. We can switch order. Who's the next big Marion? Maybe we do it this way. We switch order. So Marion Farcy will go now then. If we need some more time, Maxime, to fix this, okay? Does that work for you, Marion?
Yeah, sure.
Okay, let's do this then. Okay, so okay, so now we have the next speaker, Marion Farcy, who will talk about the role of cosmic wave feedback, I believe.
Yeah, sorry, that's not the first slide.
No, don't worry at all. Yeah, sorry for
okay,
this
yeah.
change, so to speak.
Marion, we are seeing the speaker mode.
Yeah.
Okay, sorry.
So you need to switch. So
maybe I can.
If you click on play,
yeah, so just click
again on play, and
that's
you
what
have
I
a
did,
double
actually.
arrow at the click on play, and then at the where you have the, now it's good. Yeah.
Yeah. Okay, fine. Perfect.
Yeah, thanks.
So you
Okay.
can hear me and see the slides.
Yes, please go ahead.
Okay. So I am Marion Farcy, a third-year PhD student working at CRAL with Yoki and Johan. And I'm working on radiation magneto hydrodynamic simulation of cosmic ray feedback to investigate the role of cosmic rays in the evolution of galaxies. So to give you a little bit of context of why we're interested in cosmic rays, I'll first come back on the notion of feedback, as it's an essential component of galaxy evolution, but yet not fully understood nor fully implemented in numerical simulations. So in simulations, without any feedback channel, the gas would cool and form stars way too efficiently compared to what can be observed. And we can compare simulations to observations through galaxy luminosity or galaxy mass functions or stellar mass to halo mass relation. And I've put here a cartoon of such relation, where basically at any halo mass, where we can infer the stellar content of the galaxy hosted in it, and that's a green curve in the observations. And so in simulation, in purple, without feedback, we would end up with too many stars formed at any galaxy mass. So we need to account for several feedback channels, the ones who are involved in the regulation of star formation, and I've put here a non-exhaustive list of them. And among these feedback channels are cosmic rays. So cosmic rays are charged particles, mainly consisting in protons with energy around giga-electronvolts that are accelerated in the supernova shock rays and will propagate with gas through advection and along magnetic field lines through diffusion. There are two main parameters that govern their energetics and propagation, which are the fraction of the kinetic energy from supernova explosion that goes into the acceleration, and taken to be around 10% usually, and the diffusion coefficient, which is kappa, which makes the link between the flux of cosmic ray and the cosmic ray pressure gradient, so their force, and that express in a way how easy for cosmic rays it is and how fast they can escape from the galaxy where they are accelerating. So in simulations, when we add them, we are adding an additional pressure term. And because cosmic rays undergo a diffusive process, they leak out from the dense to the more diffuse regions of the galaxy, where they will interact with gas and so can heat it through collisions or streaming losses. And all of this have the ability of disrupting ice and clouds, and so altering the star formation, but also alter the circumgalactic medium gas properties. And so we can wonder how and to what extent cosmic rays play a role in regulating galaxy evolution. So to answer these questions, I will present you first results I had with Idealized Galaxies, and so quickly going through the setup adopted in the simulations. So of course we are using the Ramses code, and including radiation propagation through Ramses RT, so that we can model the interaction of radiation with gas and have the so photoionization, heating, radiation pressure, which are feedback channels. We use the image dissolver, and cosmic rays are evolved using the advection diffusion prescription with a diffusion coefficient, a fiducial value of 10 to the 28 centimeters squared per second. And finally, we adopt state-of-the-art star formation feedback models that have been presented just previously. So for the stars, gas is going to convert into stars following a local star formation efficiency that depends on the properties of the gas. And about feedback, so that's the mechanical feedback prescription. When supernova explodes, we inject the correct amount of momentum or energy, and that's regardless of the resolution. And that's the three idealized galaxies we are going to focus on in the first part of this talk. So you have face-on hydrogen column density maps of them, 2 dwarf galaxies and 1 Milky Way mass galaxy. And you can note that the intermediate mass galaxies has already been studied in a paper from Goa Ardashian and Yoann Dubois. And we are here extended their study with additional physics. And so each of these galaxies are embedded respectively in a dark matter halo of 10 to the 10, 10 to the 11, and 10 to the 12 solar mass. And we have a maximum cell resolution of 9 parsec for the dwarf galaxies and 18 for the most massive one. Okay, so we can now switch to the results. And I'd like first to show you the impact of cosmic ray feedback on the gas and the galaxy morphologies. So here I'm showing again hydrogen column density maps, face-on and edge-on, focusing on the intermediate mass galaxy, but the same kind of maps and results occurs also for the 2 other disks. And so you can see that when we include cosmic ray feedback in the right, it tends to have a smoother gas distribution, and also that the gas is going to be thicker due to the additional pressure that cosmic ray exert on gas. And so not only they have an impact on the gas distribution, but also on temperature. So if I show you edge-on maps of the temperature, you can see with cosmic ray feedback that the gas distribution tends to be much colder than if we do not include cosmic rays in the same galaxy. So with those results, we could wonder how they are going to impact star formation. So I'm showing here star formation rate as a function of time for the lower mass galaxy first, and you have a set of 2 curves for the galaxy with in purple and without in-range cosmic ray feedback. So star formation is quite dirty to our model, and you can notice that with cosmic rays, we can suppress star formation by a factor of 2 or so. And so if I increase the galaxy mass, so in the intermediate mass one, that's the same factor 2 that can be found, even though at the later stages of the galaxies, you can notice that the 2 runs give similar star formation rate values. But now with the Milky Way mass galaxy, cosmic ray feedback tends to be inefficient in suppressing star formation, as you can see that the orange and purple curves are almost the same. So that really we have a decreasing effect of star formation efficiency in suppressing star formation with a higher galaxy mass. And we can see this effect in another way. So here I'm showing the density of the gas in which star particles are located. So that's as a function of the age of the stars. And we are increasing the galaxy mass from left to right. And while for the 2 dwarf galaxies, you can see that stars are going to form or explode in more diffuse environments when we have cosmic ray feedback. That's not the case anymore for the Milky Way mass galaxy. So just as supernova feedback starts being inefficient in high mass objects, it seems like cosmic rays also cannot impact that much the properties, so the smaller scales in the ISM of the galaxy. And from this face-on surface density, star formation rate surface density map, sorry. That's this illustrating that when we add cosmic ray feedback, we have less star formation clumps, and especially less massive, but that's for the two dwarf galaxies only. So in the beginning of the results part, I showed that cosmic rays have an impact on density, but also on temperature. So I propose you now to have a look at the outflows and the temperature decomposition. So that's the outflow rate evolution with time for one of the galaxy only first, and same as before, two curves with and without cosmic rays in purple and orange. And in time, when we have them in the simulation, we increase the outflow rate. And for star formation, it was depending on the galaxy mass. But now if we look at the three galaxies of a sample, we can see that increasing the outflow rates with cosmic rays occurs at any galaxy mass. So that's a result which seems to be independent of the mass of the object. So that's due to the fact that in the simulation, if we add cosmic rays, we add pressure term, so that we can help driving more gas. And because cosmic rays are modeled through a softer equation of state with a smaller adiabatic index, so they will suffer less losses upon adiabatic expansion. And when they lose energy, it's converted into thermal energy. So in the end, adding them really helps maintaining and energizing winds at larger distances and on longer timescale. So now if we look at the proportion, the fraction of outflows which are colder than 10 to the 5 Kelvin, so the cold outflows, so that's what's shown here as a function of time. If we focus on the orange curve first, you can see that the higher the galaxy mass, the lower the fraction of cold outflows. So really the outflows are dominating by the hotter phase. While if we add cosmic rays at any galaxy mass, the outflows are now completely dominated by the colder component of the outflows. So that really adding them change completely the properties of the gas, which is expelled from the galaxy and tends to be much colder. Okay, so even though I'd like to emphasize the fact that the results I just showed are sensitive to the way we model cosmic ray diffusion through their diffusion coefficient. So just as a reminder, kappa, which is the diffusion coefficient, expressed in a way the time during which cosmic rays are confined in the galaxy. So the lower the value, the longer they are confined. And so for a longer time, they can interact with gas and so suppress star formation. So that's what we see from this plot, that the stellar mass at the end of the run, so at 500 milliyears, 4 different values of the diffusion coefficient, which are usually taken in simulations to previous observations. So the orange crossed are for the 3 galaxies without cosmic rays. And you see that for the lower kappa value, we can suppress more star formation. And then when we start to increase it, we finally end up with a suppression efficiency, which is almost the same as supernovae only. But for the Milky Way mass galaxy, you can notice that changing the diffusion coefficient is not impacting that much the stellar mass. So that really is at high mass galaxy, cosmic rays don't do much on star formation, no matter the way we are propagating them. But still, they are changing the amount of outflows. So if I now switch to the same plot as before, outflow rate, but now depending on the value of kappa we adapt. So if we focus first on those 2 crosses, so no cosmic rays in the Milky Way mass galaxy and a low diffusion coefficient, you see that we are now actually counterproductive in launching winds. And we can explain this looking at those 2 age-on maps of hydrogen column density. So with cosmic rays, we still puff out the disk, which is thicker. And so the gas is actually denser, so it will be more difficult to push it at larger distances. And so at 10 kiloparsec, where these outflows are measured, we have actually lower outflow rates. Then if I increase the value of the diffusion coefficient, I'm consistently increasing the outflow rate. And you can see that the gas distribution around the disk tends to be more and more extended.
3 more minutes. Okay.
And finally, if I use the most extreme values, which is adopted in the fire team, for example, so 3 × 10⁻⁹ centimeters squared per second, we are not that much increasing the flow rate. Actually, it slightly decreases. And you can see that now the gas distribution so it's more and more diffuse. So because cosmic rays escape more quickly from the galaxy, they start acting at larger distances later, where the gas is already more diffuse. And so as a result, we are not increasing again and again the outflow rate. So that's the conclusions from the idealized galaxies. And I'm going to come back on it just after. But just to let you know that we are now switching to a more realistic context where we have cosmological info. So we are focusing on halos, zooming halos from the 620 cosmological simulations at high redshift. And if I have time, I can show you quickly what we have. So that's ongoing work. And that's one of the halo we are zooming in. So you have density maps, temperature maps of the same halo without and with cosmic rays. And just as what we saw with the idealized galaxies, when we have cosmic ray feedback, the gas distribution is smoother and also colder. And if I quickly show you star formation, so that's the stellar mass, evolution with time for 3 of the zooming halos. So as before, again, as for the idealized galaxies, cosmic rays can suppress star formation by something like a factor of 2, and especially their efficiency decreases with increasing halo mass. So I will leave you with my conclusion slides, where we saw that cosmic rays help producing a smoother and a colder gas distribution, that they can alter star formation rates for dwarf galaxies only and become efficient in high mass objects, but that in any case, they can help driving more and colder outflows, even though quantitative resist depends on the way we model the propagation. So those results are really part of a paper which hopefully will be soon submitted. And what we'd like to do next, because we saw that cosmic rays impact the density of the gas, so we wonder how they can impact the way radiation is absorbed, is to look at the impact on the epoch of ionization itself. So thanks for your attention. I'm done if you have any questions.
Okay, thank you very much. Questions for Marion? Julian.
Yes, thank you for a very nice talk. I have tons of questions, but I want to refrain myself. I'm just going to ask one. I noticed that you showed that the amount of outflows that you get from the cosmic rays does not depend on galaxy mass, but you also showed that the star from the stellar masses, amount of stars formed is not different with and without cosmic ray in the Milky Way galaxy. Yeah. So I was wondering where you measure your outflow in these galaxies, how far from the disk, and do you think this result happens because in the Milky Way galaxy the gas shoots up but then rains back on the disk and maintains the same star formation rate, or am I missing something?
Okay, so they are measured at 10 kilo/sec, and the thing is that you can see that the mass of outflowing gas is pretty much the same for the intermediate or Milky Way mass galaxy. So even if we can drive more gas away, indeed, it's unlikely going to affect star formation. It will be needed to eject much more, a higher content of gas out of the galaxy. So indeed, it can be escaping and then fall back into the disk again, and that's not an amount consequent enough to impact star formation.
Thank you.
Okay, Arturo.
Hi, I do have a few questions as well. Really nice talk, thank you. So basically, my first question is, on your isolated runs, do you know more or less the time scale it takes to fill the whole disk with cosmic rays?
It depends on the diffusion coefficient, of course. I'd say that by something like 300 megayears, you can fill the whole box in the most extreme case.
No, but the disk, more than the
oh, the disk. Yeah. I don't have a precise value to give you. It's between 200 and 300 megayears, I'd say.
Okay, so it's a lot, because I think in Joan's paper they go all the way to 250, so it means that they just fill the disk.
Yeah, indeed, they stopped earlier the run.
Yeah. Okay, so my second question is basically, have you looked at the dark matter distribution, whether there is an impact?
I did at some point, but not that much actually. So it's not a super strong feedback cosmic rays, I mean. So no, the dark matter profile didn't change much.
Oh, nice. Okay, but since you're changing the outflows, I would imagine maybe the dark matter it's being affected. But okay, thank you. Really nice, huh?
Okay, one key.
Okay, hi. Thank you for your great presentation. Sorry if I missed, but can you? It was kind of interesting to see how kappa can affect the results. And I was wondering, do you have any plan to implement a cosmic ray spectrum which might have an energy-dependent kappa on? Yep.
That's not planned yet, not by me actually. Maybe there are people working on this in a laboratory in Paris. I heard about that. So yeah, indeed, it would be super interesting to model the diffusion coefficient with energy or momentum. Actually, so there is a paper from today talking about that. But I'm not sure I will have time to do this myself in my last year of PhD.
Thank you.
Okay, I have a question, and maybe you said this early on in the method slides, but are you doing anisotropic diffusion or is it an isotropic coefficient?
It's anisotropic, and I didn't mention it, I think. Yeah, sorry about that. Yeah, it's anisotropic.
Okay, so and it's a ratio of 1 to 10 or something in terms of the coefficient, if it's orthogonal to the field lines, or how? What's the?
What are you talking about?
So it was isotropic or anisotropic?
Yeah, anisotropic, and you were talking about the.
Yeah, because so then what are the values then for the? So the ones you quote here, is that the one parallel to the field lines?
That's a parallel indeed. Yeah.
Okay. And maybe another quick question then for the cosmological runs, which value of kappa did you pick then?
I chose the same values as for the disk, so it's my fiducial value, let's say. Yeah, so it could change slightly quantitatively the results we're going to have, even though for star formation, I think it will behave the same as what we saw in the disk.
Okay, great, thanks. Okay, so I think we should move to the next speaker. Thanks you, Marion, for this talk. Maxime, are you ready to go?
Can you hear me now?
Yes. Okay, very good. So please share your screen then.
So which screen is it? Here. Share. That should be good.
Great. Okay. So and Maxime will talk about the CGM as a constraint for star formation and feedback subgrid models. Please go ahead.
Thanks. So hi everyone. I'm Maxime Rey. I'm doing my PhD in Lyon in France with Jeremy Blazo. And I'm studying galaxy formation with Ramses simulations. So in this talk, I will present to you ongoing work where we're trying to figure out whether the CGM may help to discriminate these different models of star formation and feedback. So the evolution of galaxies is complex and involves many processes on many scales. There's accretion of gas inflows, which bring gas into the ISM and fuel galaxy growth. Gas in the ISM will then fragment, condense intermolecular clouds, which in turn will fragment and collapse into stars. The massive stars that are formed can generate different forms of feedback, such as photoionization, radiation pressure, or supernovae explosion. And combined together, these processes disrupt the molecular clouds and may trigger galaxy-scale outflows, which removes gas from the galaxy. Some of it is heated up to high temperature and ejected outside the dark matter halo and will never come back, but a fraction of it is pushed away less strongly and may fall back to fuel future generations of stars. So the evolution of galaxies is a very intricate process, and very importantly, from the viewpoint of galaxy simulations, the key processes that are here, so star formation and feedback, have to be described through subgrid models. And what's often done in such simulations is to calibrate them on the stellar mass to halo mass relation. The lines are from observation and different points are from different simulations. And what we see here is that even though many have different physics implemented in different manners, even with different resolution, many can match in stellar mass. So there must be something complementary on which we could calibrate them. And a hint comes by looking at the mass loading factor, which is here shown against the halo mass. So it's the ratio of the outflow rates against the star formation rates, and clearly depends strongly on the subgrid models I mentioned earlier. And what you see here is that even these models are calibrated to have the same stellar mass, there is a huge dispersion in the mass loading factor. So this is the hint that they could be distinguished maybe by looking at the CGM. So my strategy is to look at one galaxy, the same galaxy with the same code, so Sphinx with RHT and non-equivalent chemistry, the same initial conditions, same refinement scheme, and then on this galaxy test different subgrid models for star formation and feedback. And then after calibrating them on M star, trying to distinguish them by looking at their CGM. So the different models I'm looking at are mainly from Kim et al. 2015 and Kretschmann 2020, and an extension of the first one. So the main difference is in these two. First, for star formation, the equations are a bit different. And the most important point is that turbulence is really important for star formation, and it's considered differently in these two models. In the first one, an approximation from the surrounding cells is made to consider turbulence, whereas in here, there is a subgrid turbulence model for star formation. And concerning the feedback, both rely on a very similar method, which was presented by Arturo, and which is mechanical feedback. So basically, depending on the regime of the supernova you're considering, you're using different equations. So in the first case, these two regimes are split by the mass swept up by the supernova, and then depending on the regime you're in, you're injecting a different momentum in the neighboring cells. And in the second case, it's different because you automatically inject thermal energy, and then if the cooling radius is not resolved, you compute a momentum which you don't inject like previously in the neighboring cells, but which you add to the Euler conservation equations. So these are two different implementations of basically the same thing. And the third thing I'm looking at comes from Anderson et al. 2020, who saw that runaway stars could have an important impact on the outflows. So basically, when you form stars, you give them the velocity of their host molecular cloud. And he saw that by giving them an additional kick, they could move to lower density region and then have stronger outflows. And it was also seen by Edouard Tollet in cosmological simulations. So it was a really interesting thing to look at. The first thing I did was testing several different parameters on idealized simulation of isolated disks, The first one was a few times 10 to the 8 solar mass and stellar mass. Second one was 10 times more massive. And after understanding how it worked a bit, I calibrated them on stellar mass and saw if that held onto a more massive galaxies, and then moved on to cosmological zoom-in simulation. The box size of this simulation is 30 co-moving megaparsecs. The dark matter halo is a few times 10 to the 11 solar mass. The stellar mass is 10 times lower. And the halo radius at z equals 1 is 100 parsec. So the simulations were run down to z equals 1. And the zoom region, is 1 virial radius, and the maximal resolution in it is 20 parsecs. So I'm showing you here the same plot as previously, so the stellar mass to halo mass relation. And you can see the different kind of points represent the different simulations, and they are color-coded by redshift. So it goes down to redshift 1. And in here you have the observational relations. So at redshift 1 and at redshift 0 in dark. And what you see is that there's a difference in those. If you look more closely, it looks like there are two regimes in the evolution of the stellar mass to halo mass relation. Well, it looks like since this is the point from which the galaxy is quite massive, this might be due to the lack of AGN feedback in the simulation. But nonetheless, what we wanted here was to calibrate the three simulations at stellar mass. Well, that's the case, so that's fine. So we look then at the CGM by hoping to find differences, and we look at the inflow rates and the outflow rates. So here we have the inflow rates against time and the gas inflow rate and the dark matter inflow rate. And you see a small variation of the gas inflow rate. And I first thought it was due to preventive feedback, but actually it's the same as the dark matter inflow rate, so it doesn't seem to be it. But the most important point here is that they're all the same. And if we look at the alpha rates, well, they're also all the same. So it doesn't look like we can distinguish this model by looking at this flow rate. But we can wonder, even though the flow are different, maybe we can differentiate them by looking at the gas content. One might be colder or hotter. And also, how does it compare to observational constraints? So what I did was look at different ions, so namely MD2, H1, C4, and O6. I did so by post-processing the simulation and computing those with Chrome, following a method from Valentin Mauerhofer. And in here, you can see the phase diagrams with mass-weighted color codes depending on the ionic species considered. And here, the probability distribution function. So you see that MD2 and H1 are tracing cold gas, C4 is tracing warm gas, and O6 is tracing the hot gas. So the observational constraints I looked at are column densities, so radial column densities. So first, for the cold gas H1 and MD2, you can see for H1 that agreement with different observations is really good. And it's also the case when looking at the first few kiloparsecs in MD2. But if you look further away, there's a significant difference between the median and the observations. And this might be due to a detection bias, I think, because, well, these column densities are very low and can be detected. And also, if you look at the spread there is here, well, the observation matches with the spread. So I'm currently looking into it. And the point was to differentiate the models. And well, once again, they are very similar here. And there's a small difference here, but I'm investigating it, and it might be due to satellites moving closer to the galaxy. So our last hope is by looking at warmer gas. But if we look at warmer gas, well, the three simulations are actually the same, and the spread is even lower, both for C4 and O6. There's also a consistent difference of 1 dex between the observations and the simulations. This was seen in literature for several years. And I'm currently looking into it and looking why is that, and trying to understand if the cause for this difference is the same as it was seen. So basically what I've seen is that, well, the models can't really be distinguished by looking at the CGM. They have the same stellar mass, outflows, radial column density profile, same gas contents, but I still found some differences which weren't shown on the CGM. The first one is in the star formation history. So here you have the star formation rates against time, and you see that Kretschmer's model in orange here is way more bursty than the other two models. And this difference seems to arise from the place where the stars form. So in this plot, I show you the density of the cell in which the stellar particle belong, and this against the stellar age. So if you look in the first few megayears, you see where the stars form. And systematically, you see that in Kretschmer's model, stars formed in a denser environment. His model allowed the gas to collapse more before forming stars. So once it was quite dense, it formed stars which were more massive, as the mass of the stars formed depend on the gas content of the cell. And this provoked really a huge burst of star formation. And another interesting point looking at this graph is that runaway stars are kicked and are supposed to move to a lower density region. But you see here that it's not the case at all. It's the opposite. It seems like they stay in a slightly denser environment. So it doesn't look like they have a big impact on the simulation. And the second difference between the models is in the morphology of the simulation. Sorry. So down to redshift 1.3, the simulations evolved in a very similar way. So here you can see them. You can see them in density, in temperature, in stellar surface density. And from redshift 1.3 down to redshift 1, in Kretschmer's model, there is an extended disk that started to develop. So I ran this simulation, this one a bit further down, and down to redshift 0.8, this disk stayed, and it didn't form at all in the other simulation.
You have 3 more minutes.
Yep, thank you. So that's really intriguing because, well, they supposedly have the same merger history since they have the same initial conditions, but this doesn't show at all in both schemes, in both models following, in both schemes models, sorry. So this made us think about a second paper from Kretschmer from 2020, where he saw 2 different galaxies, and one became bulge dominated, sorry, and one became disk dominated. And he inferred that this was due to how the gas accreted on the galaxy. So by looking here at the cold gas and its mass-weighted angular momentum, he saw that the gas accreted counter-rotatively in the case of the bulge-dominated galaxy, but additively in the other case, and constructively, sorry. And if you look at the simulation I just showed you earlier, well, we have this disk, so it seemed to correspond to this case, but you can see that it is counter-rotating, so it does not seem to be the cause. If you have any ideas on why that is, if you have any, I'm open for discussion. And so to conclude, well, there are differences in the model. So for example, the turbulence consideration, the equations are slightly different in star formation. You have different implementation of the momentum feedback, and you have runaway stars, but these doesn't seem to be, we can't distinguish them through the CGM flows or contents. Yet we still found disparities in them, which is really interesting. But in hope to distinguish them, I'm currently looking at another constraint, which comes from the Megaflow collaboration. So they saw that the outflow seems to be biconical in observations. And here you can see the detections of MD2 against the azimuthal angle from the major axis. And you can see that there clearly seems to be a distribution. So I'm currently investigating if we could distinguish the different simulation by looking at those. And that's all for me. Thank you for your attention.
Thanks, Maxime. Questions? Okay, I will begin with my friend on my right here, Eric. Go ahead.
So let me ask the question through Oscar's mic to sort out problems with echoes and stuff. So thanks for a great talk, very interesting results. So I'm a bit interested in, like, how do you do the runaway model? Because I find quite different results compared to what you show.
So initially, Edward Collet studied it with the model from Anderson et al., which was, there's no video. I thought I'm stop sharing and sharing the video again. Sorry. He was looking at a distribution of the kick, which was depending on the radius, and also tried to use a uniform distribution, giving a uniform kick of 50 kilometers per second. And so that this one had a more drastic impact. So he advised me to opt for this more drastic impact if I wanted to see an impact. Well, an impact. So it's a uniform kick of 50 kilometers per second, and not exactly the same as Anderson et al.
So do you apply it to all the star particles? Or
Yeah.
Okay.
Yeah.
Thank you.
Okay, Luke, next question.
Hi, Maxime. Thanks for a great talk. Very interesting. I know it's only like a tangential plot that you showed, but the stellar mass halo mass relation you showed and comparing it to Baruzzi and Moster. I'm interested to know if you looked at this at the color scale is high redshift. Okay, so you're always slightly above it. Okay, thanks. That's answered my question. See you again.
Okay, perfect.
Thanks.
Okay, Tyson.
Great talk, Maxime. So you mentioned that we need hotter, stronger and hotter outflows to reproduce, that was 06, is that right?
I'm not sure of the cause yet because I'm not familiar enough with the topic. but that's what I thought I understand from what I've seen now.
Yeah, so I'm asking because Marion showed that we're going to get warmer outflows by having cosmic ray pressure, and this seems to be going opposite direction. Is that right?
Yeah, definitely. So by adding cosmic rays, looks like it would go further out. But so maybe the origin of this difference is something else, and maybe one thing I'm going to look at is maybe the reservoir in O5 is huge and O6 is really unstable, so it's not tracing it correctly enough. But I'm really not familiar enough yet with this. But yeah, Marion might hinder me in this hope of matching observations.
Okay, thanks.
Can I add something about that?
Yeah.
Just if I'm not wrong, Maxime is using the supernova boost prescription such as done in Sphinx, so that there are 4 times more supernova explosions. And as I saw, this leads usually to hotter gas and hotter outflows. So that's causing the same direction.
Yeah.
Basically, thermal feedback tends to produce hotter gas, and that's probably increased furthermore in this case.
Yeah, definitely.
Okay, Julian.
Yes, nice talk, Maxime. I had a question about your counter-rotating gas angular momentum. So if I look at the naively, if I look at this galaxy, I see that compared to the galaxies with Tayson's model, you have a dense central core and a very extended disk, and the dense central core is a little bit less extended than in Tayson's model. So is it possible that that basically you have the same amount of angular momentum in both, but one is there's much more mass concentrated in the center in the Crashmare and Tessier, and then a more diffuse disk, but then overall there's the same angular momentum in both there?
Well, I don't think that's the case, because when I looked at the evolution of the density profile through times, it didn't seem to rise as a striking difference. But so
and also you say counter-rotating, but you can have two things can happen, right? The central disk can be counter-rotating compared to the outer disk as well. So when you say counter-rotating, up to where do you measure the angular momentum to say counter-rotating? I see a blue dot in the center of your galaxy. It looks like, so, there could be multiple disks with multiple components, right? It looks like this could be the case, right? You can have an outer disk rotating in one direction and an inner disk rotating in the opposite direction.
Yeah, but still, I'm not sure I see your points here, because, well, I don't know how to put words into it. But the thing is, why was it created in one of the in only one of the 3 simulations, even though they have the same initial conditions?
Because the outer disk is created by the inflow, but the inner disk is the angular momentum is redistributed through all the processes that you have, and which is going to be different in the different simulations. That would be my guess, but anyway, it's a guess.
Okay.
Okay, Yuan, last question.
We can't hear you, Yuan.
Yeah, I was muted.
Okay.
Just going back to your line diagnostics, the O6, etc. So you have not considered, the only source of feedback you've considered is stellar feedback, but probably for those Mochimassis, you can have an agent in the center, probably not very important for regulating the stellar mass.
Sorry, I don't really hear you that well. Can you move closer to
Okay, so you have only considered stellar feedback, but you can have a central source from an AGN, which won't modify probably very much the central stellar mass, but this can have a huge impact on the CGM properties.
Okay.
In terms of change of temperature density. I mean, what is your guess on this?
I really don't know much about AGN, so that's a really interesting comment that AGN might change that. And I think I've looked at it while reviewing a paper from Oppenheimer, but I haven't dwelt that much into that yet. But it indeed seemed like it could have an impact on this, because there's also fluctuations. He mentioned that fluctuations in AGN might increase the O6, and I don't remember precisely why. But that's definitely something that might have an impact here.
Okay, we are running short on time. Harley, can we park that question for the lunch break? Is that okay? Or
yeah, no problem.
Yeah, okay, let's do that. Okay, thanks, Maxime. The next speaker is Arnaud Durocher. Please share your screen.
I will share my screen.
Arnaud will talk about some new exciting hardware agnostic AMR codes, a code Diablo for the Ramses community. So please go ahead.
Yes, so I'm going to talk about something a bit different from what you've been hearing until now today. So I'm going to talk about Diablo, which is a new hardware agnostic AMR code. Yes. So it's my first time at the Ramses user meeting. So thank you for having me here, even if I'm not talking about really about astrophysics now. So Diablo, for a bit of context, I'm going to talk about the GENA group, which is a work group that have been created to find ways to overcome the barrier to exascale that the astro community is facing and the Ramses community as well. To go towards exascale, we have a few challenges, mainly the new architectures, the new ARM processors and the new GPUs that the future machines are going to use. And those machines are going to be bigger, and there are some challenges with that also. The GENA group is focused specifically on the astro community challenges, that being the adaptive mesh refinement for the simulations that you need, the multi-physics simulations, and also the large data production that the simulations, those simulations are producing. So what is Diablo? It's a new modern and modular AMR code that is hardware agnostic, and it is aimed at the astrophysics community and more specifically the Ramses community. So it's written in C++, and it has an applicative layer, plugins that will allow you to add physics modules. It's hardware agnostic thanks to the Cocos library. That means with the same code, you can run on CPU or GPU. And it also does like Ramses adaptive mesh refinement. We are using a library called Pablo for that, but we are also developing our own AMR algorithms that will work on CPU and GPU. It's aimed at the Ramses community, but not exclusively. It will have in the future the same features as Ramses. For now, we have a hydro solver. We will add in near future self-gravity and then particles, etc. So the architecture of Diablo is created around a central Diablo platform, and there are applicative layers where physicists can write their own initial conditions, solvers, etc., and use the Diablo platform that provides the tools to iterate over the AMR tree, etc. Diablo in the backend uses functional libraries, namely Cocos and Pablo, that in the backend use parallel programming models such as OpenMP, CUDA, or MPI. A word about Cocos, which is the core of the Diablo platform. Cocos, it's a C++ hardware agnostic parallel programming model, and it's developed in the US for the new exascale architectures that will be installed there. It has a number of backends, such as OpenMP, CUDA, and other backends for next generation hardware. The principle is that you write your kernels using parallel for instead of for loops, and you use C++ lambdas to describe what has to be executed on each element of your array. And you have arrays that are abstract multidimensional arrays, like in Fortran, called CocosView. You select at compile time which backend you want to use if you want to compile for CPU or GPU. So what you have to remember here is that Cocos allows us in Diablo to compile the same code for different architectures. So here is what it looks like. So you have the parallel for that replaces the for loop, and you describe with a lambda the code that you want to execute for each of the elements of your array. That here is a 2D array. We also use another library for the AMR tree, which is called Pablo. It's part of a bigger library called BitPit. And it performs all the algorithm necessary to remesh the AMR mesh. It uses MPI parallelism, so it decomposes the tree in different subdomains, and it can also perform MPI communications of the ghost cells between the domains. It's a bit different from the octree in Ramses because it uses a so-called linear octree, meaning that you only store data on the leaves of the octree and not on the whole node, on every node of the octree. So in Diablo, we implemented some features, not all of them yet. It lacks some features compared to Ramses, but we implemented with the same geometry as Ramses, namely the Cartesian AMR, with a twist because we used block-based AMR. I'll talk about it later. We implemented the Hydro solver with a finite volume Muscle-Hancock scheme, like in Ramses. And we implemented static gravity with a static gravity field. And we are right now implementing self-gravity in Diablo. We want in the near future to add particles in Diablo also. You can visualize the result of your simulation with ParaView, thanks to the HDF5 XDMF output. And we are also working on compatibility with other tools that you might want to use later on. The parallelism, as I told you before, it's a hybrid MPI plus Cocos parallelism. So with MPI, we do the domain decomposition, load balancing, etc. Through Pablo. And we write the compute kernels on each MPI process with Cocos that can run on CPU or GPU. Now, a word on what is difficult with AMR on GPU. So the challenges of AMR on GPU is that, first of all, there are no GPU AMR libraries available. So the Pablo library that we use, it's CPU only, and the approach in Ramses is not really suited for GPU. It has been tried to port Ramses to GPU and the Contrat de Progrès at Idris, I think it was last year or 2 years ago, and it was not really suited for GPU. So the performance challenges on GPU for AMR is to find the right data structure for the AMR tree, to be able to find the neighborhood of the cells, to perform the stencil algorithms needed, for example, for all the solvers. And we also have to be careful of the transfers between CPU and GPU. We don't want to transfer the AMR tree between the CPU and the GPU too often because it's really expensive. We don't want to transfer too much, too many MPI buffers for the MPI communications, etc. So some of the solutions we have implemented in Diablo. The first one is the use of a block-based AMR. That means we at the leaves of the tree we use a Cartesian subgrid. As we can see here, here is the cell-based AMR as in Ramses, and here is the block-based AMR. It has two main advantages for GPU. First, we have Cartesian subgrids, which allows more regular access for GPU, which is good for GPU. And also, we are reducing the depth of the AMR tree, which will reduce the cycle, the cost of the AMR cycle, which is really important. We'll see that later with the benchmarks. We also implemented our own data structure for the AMR tree. We used the linear tree like in Pablo, and we used a hash map to store the AMR tree. Conveniently, Cocos provides a GPU implementation of an hash map that we used for that, and that allows access in parallel and with great performance to the AMR2. Now, a set of benchmarks with Hydro only. First, the single node performance. So it's a really simple benchmark because it's a 3D set of blasts. We have 3 active AMR levels, and we are running Diablo on CPU and on GPU, and we are comparing it with the same test case in Ramses. First, on CPU, we ran Ramses on Janzé, which is the French machine, the French GPU machine at CNRS. We ran Ramses on 40 cores because there are 40 cores on each node. So we ran Ramses with 40 MPIs, and we ran Diablo with 4 MPIs with 10 core each in MPI plus OpenMP. And we see that the time to solution of Ramses here is higher than the time to solution is in Diablo for this particular test case. And we also see that the block size of the AMR block, the block AMR, is quite important for the performance. On CPU, what takes the most time in the simulation, it's the Hydro solver. But we will see it's a bit different on GPU.
You have 3 more minutes.
Yeah, thank you. So on GPU, we are way faster. So here we run on the same machine, Janzé, with one NVIDIA V100. And we can see that we're on this particular test case 10 times faster than Ramses with 1 GPU compared to 1 full node of Janzé. A quick note: Janzé nodes have 4 V100 GPUs. So here we are. The GPU can accelerate the computation quite a lot. Well, now another benchmark is to measure the MPI scalability of our code. So we did basically the same blast benchmark, but we replicated the blast to have 4 blasts per compute node. So here is 1 blast, here are 2 blasts, etc. So we are the volume of the simulation is growing with the with the number of nodes. So the times 2 solution with a fixed number of iteration should stay constant over time. Well, if you want more detail, you can ask during the questions. Here is the scalability of Diablo when compiled in a hybrid MPI plus OpenMP mode. So we can see it's quite good up to 1000 MPI process. That's 10,000 cores because we have 10 cores per MPI process. And on GPU, we also have a good scalability until 512 GPUs. We can see that it's quite faster than with twice more CPUs. No, CPU node. I also have the same data as a time to solution, but I'm not going to give more detail on that. So in conclusion, I presented you Diablo, which aims to be modern and modular, that is compatible with CPU and GPU and probably many more future architectures thanks to Cocos. I talked about the challenges of AMR on GPU, and I hope that Diablo will be for you, for the Ramses community, a solution for exascale and to simulate on GPUs. Then I showed the Hydro demo with the AMR block and the Hydro solver, and I showed that the performance was competitive with Ramses in a single node, even on CPU, and it was scalable up to 512 GPUs and 10,000 CPU cores, which, by the way, is the max allocation on the Janset machine. So next, we want to improve Diablo by adding physics, self-gravity particles, for instance. We want to add some optimization to the solver, for example, the multi-time step optimization, etc. And of course, we want to collaborate with the community, the Ramses community, and the astrophysics community as a whole. So if you want to try Diablo, contact us, and we can work something out. Thank you for listening. And if you have questions, I'm going to answer them now.
Thank you, Arnaud. First question from Sam.
Hey, thanks. Yeah, so yeah, this is super nice. So having used C++ for a while, a while ago, it's kind of verbose and can be difficult, if you're not using the same coding standards and so on. So is there a sort of indication that it'll be easier to kind of prototype stuff for, physicists who are not necessarily programmers?
Well, we are working on having interfaces for the AMR that are going to be easier to use than just C++ code. So we'll have iterators and things like that to ask for the neighbors, etc. So we want to make the job easy for physicists. Here we have the platform, so physicists are going to write their own kernels, etc. with the plugins. And the plugins will use interfaces to iterate over the AMR mesh without directly writing some Cocos code, for example.
So would it also be possible to put it into something like a Muse, which is this kind of Python layer over different simulation codes, or is that something that, I don't know if you know about this? Or...
Yeah, maybe in the future. For now, we are concentrated on adding the physical features. Because there is a lack of a lot of solvers for now. But yeah, that's an idea that could work. Yeah.
Okay, thanks.
Right. Any further questions? All right. I think we have arrived at lunch now. So thanks, Arnaud. Thanks to all of the morning speakers. Very interesting talks. We're going to return at 2 p.m. for more Galaxy talks, and the chair then will be Sam. Okay. All right. See you in an hour and a half, roughly. Okay.